In this video, we are going to start looking at the reactivity of those intermediates that we talked about recently, enols and enolates. At first, we are going to be talking about alpha halogenations under acidic conditions. Understand that under acidic conditions, ketones and aldehydes are going to undergo alpha halogenation. As you can see, the reagents for these transformations is going to be hydronium, which is going to be our source of acid, and bromide. As you can see, that's just molecular bromine. I shouldn't say bromide. This is just molecular bromine. Now, what is occurring, as you can see here, is that specifically that alpha carbon that I wrote in is the one that is going to be receiving that halogen. Understand that this alpha halogenation will work with molecular chlorine, molecular bromine, and molecular iodine, not for fluorine. To be honest with you, many times whenever these halogenations are happening, fluorine is going to be the one that is the least favored. Now, if we are doing halogenation under acidic conditions, that means that our reactive intermediate is going to be the enol. Let's actually explore the mechanism to observe the formation of the intermediate and the products. So, if alpha halogenation is happening under acidic conditions, understand that the first part of the reaction is going to be the formation of that enol molecule. As you can see here, we have a ketone molecule utilized in the example. In the first step of the reaction, what is going to be happening is that the oxygen in the carbonyl is going to be protonated. That protonated C double bond O, understand that then it can undergo a resonance stabilized structure. And in the second step of the reaction, you can see that the water molecule is going to be deprotonating the alpha proton to give rise to the enol. Then, once the enol has been formed, as you can see, because that's what we have from the structure above, in order to illustrate the halogenation, you have to make the lone pair that is present in the oxygen move down, and then from the double bond, that's how you attack one of the halogens and breaks the halogen bond, in this case bromine. In the last step of the reaction, in order to form the alpha halogenated product, what we have to do is utilize another equivalence of the water and deprotonate the oxygen in the carbonyl to form the product. Now, in the previous example, we were using a symmetrical ketone. What will happen when you have an unsymmetrical ketone is that halogenation is going to be occurring faster, okay, at the site that we have an alpha carbon that it is more substituted. So as you can see in the following example, now we have a methyl group that has been incorporated to the alpha carbon that is specifically to the right. And when we compared the halogenation of either one of the alpha carbons that we have there, the major product is going to be specifically the alpha carbon that is the most substituted. Okay. If we think about it, when it comes to this, the major product is actually going to be resulting at that position because we are going to have an enol that is more substituted. And as you guys learned previously, when you have more substitution in a carbon-carbon double bond, if you remember to something related along those lines was the Sicev rule. What is happening is that having a more substituted carbon-carbon double bond is going to be making it more stable. The enol that is the one that forms So this enol is the one that is forming that minor product. As you can see, is less substituted. That's why it gives rise to the minor product. Let me just write a dotted line. So the enol that I have the dotted lines from, that is going to be the one that results in the major product. As you can see, alpha halogenation provides a two-step synthesis for the synthesis of alpha beta unsaturated ketones. Okay, so as you can see in this process, step 1 is going to be the alpha halogenation, and on step 2, that pyridine, what is going to do is that is going to eliminate and create that carbon-carbon double bond within the ring system. Okay, so this is called an alpha beta unsaturated ketone because, as you can see, at the alpha position and at the beta position, we have a carbon-carbon double bond. Other bases that can produce the elimination to make that alpha beta unsaturated ketone, and we're talking ketone specifically because of the example that we started with, will be T-butoxide or lithium carbonate. Now, understand that we also have the HVZ reaction, which is the Hal Fischerzelinski reaction. Okay, in this reaction, we are specifically looking at bromination. Okay, so in this reaction, we are going to be brominating specifically the alpha carbon or of carboxylic acid. Okay. So as you can see here, in the first step of the reaction, you're going to be using Br2 along with PBr3. Then in the second step of the reaction, we're going to have water, and that's how we can do alpha halogenation, specifically to a carboxylic acid. Okay, so when it comes to the mechanism, as you can see, is believed to be in the following sequence. This is a mechanism that it is still understudied. So when it comes to this, as you can see, we're going to have our carboxylic acid, and in the first step of the reaction, we are going to have the formation of an acyl bromide. So we're going from a carboxylic acid to an acyl bromide. Then it is thought that your acyl bromide is going to make an acid halide enol. That acid halide enol is then going to be reacting with Br2 and getting that bromination at the alpha carbon, and then with the reaction of water, that's how you reform that carboxylic acid. Alpha halogenation is not only found under acidic conditions, it can also be achieved under basic conditions. And when it comes to doing the reaction under basic conditions, as you can see in the following example, when we have, for example, this ketone, okay, one of the alpha positions is completely substituted, so it has two methyl groups, so the only available protons are going to be the ones in the alpha carbon that I marked with a check mark. Okay, and that's where we have the bromination. Now, if we are under basic conditions, then the enolate is going to be the reactive intermediate that we are going to be illustrating in the reaction. And as you can see in the mechanism in the bottom, if you are doing the alpha halogenation under basic conditions, the first step of the reaction will be the formation of the enolate by the base deprotonating the alpha proton on the alpha carbon. As you can see, we have then a carbon atom that has a lone pair. That lone pair can go and attack the bromine, break the bromine-bromine bond, and that's how we have bromination at the alpha position. Now, understand that under basic conditions, polyhalogenation is typically observed. So as you can see in the example that we just utilized in the previous slide, if the ketone, okay, is brominated, it will, again, if it has another alpha proton, it's going to form the enolate, and it's going to be brominating again at an even faster rate. So understand that this is just a complication that happens specifically under basic conditions. Now, understand that under basic conditions, methyl ketones are converted to carboxylic acids using excess halogen and hydroxide. This is specifically called the haloform reaction. So, overall, as you can see here, the haloform reaction is a two-step reaction. This methyl ketone, as you can see, and I'm going to illustrate, has an alpha carbon that has 3 protons. Overall, the final product of the reaction is going to be basically exchanging that CH3, that methyl part of the ketone, for an OH. Let's observe how that happens. So you can envision that in the reagents that are used in the first step, what is going to happen is that overall, that CH3 is going to be fully brominated. Then, in the second step of the reaction, what is happening overall is that CBr3 is going to be acting as a good leaving group. So when that strong base is present, then the carbon in the carbonyl is going to be attacked by the OH. The electrons are going to go up to the oxygen, and then when they come down, they're going to be kicking off that CBr3. So that's going to be our leaving group. Now, understand that in this reaction, we are forming a carboxylic acid. And because CBr3 is going to be acting as a base, then it's going to deprotonate our carboxylic acid and making a carboxylate ion along with the bromoform. That's why we have to do an acidic workup to protonate. So if we go back, this acidic workup is going to be for the final protonation of that carboxylic acid. Understand that this halogenation of a methyl ketone, Br2, Cl2, or I2 can be used, okay? And this is synthetically useful to produce a carboxylic acid from methyl ketones, okay? Now, this works best if the other alpha carbons has no alpha protons, because you can envision that if both of them have alpha protons, then that is going to be a problem synthetically, okay? Now we are going to move forward and talk about aldol additions, okay? So one of the things that we have seen before is that when an aldehyde is treated with hydroxide or an alkoxide, there is an equilibrium between the product and the reactant. But one of the things that has been observed is that depending on the base, and we already illustrated earlier in this chapter, there's some bases that just lock in the enolate, so they don't let it equilibrate to the reactant. And in the case of NaOH or alkoxide, if it's utilized, understand, for aldehydes and ketones that are not 1,3-dicarbonyls, what happens is that the intermediate is going to go back and react with the starting material, okay? So understand that when the enolate attacks the aldehyde, that's what an aldol reaction is, okay? So the product is going to feature an aldehyde, which is this portion, and an alcohol, which is this portion. Understand that the location of the OH group is specifically at the beta carbon, okay? When we look at the position along the carbonyl, okay? And we're going to be looking at the mechanisms to understand why the position of that OH is at the beta carbon from the C double bond O. So understand that under basic conditions, if we have an aldol reaction, an enolate is going to be the reactive intermediate, okay? So this is the mechanism for an aldol addition mechanism. So if we have a base, understand that what happens is that the aldehyde is going to have a deprotonation by the strong base, is going to form the enolate, and then the enolate is going to react as a nucleophile and attack the carbon in the carbonyl in the aldehyde. That is going to result in an alkoxide intermediate ion that it proceeds to get protonated to give that aldol product. Understand that the aldol addition is an equilibrium process, okay? For most simple aldehydes, the aldol product is favored. So as you can see here in this molecule, we have butanol. When it's reacting in the presence of base, specifically sodium hydroxide and water, you can see how the product of the reaction results in the aldol product. Now, understand that for most ketones, the aldol product is actually not favored. So as you can see in the bottom of the slide, if we have cyclohexanone and we put it in base, it's not going to result in the formation of an aldol product. The yield is really, really low. Now, understand that that aldol can actually undergo a retro-aldol reaction, okay? And the mechanism is basically the reverse of the aldol. If we have a base, okay, specifically, we're going to have the proton from the hydroxy that lives in the beta position. So this is the beta carbon right here. Is going to get deprotonated. Once that oxygen atom it is negative, then understand that the carbonyl group is going to be reformed, and what's going to happen is that it's going to break the bond between the alpha carbon and the beta carbon in the system. So it's going to be the bond that I highlighted in yellow. It's going to result in the formation of an enolate that can then get protonated and reform, in this case, the starting carbonyl that you have in the reaction. Now, it is important to note that if you have an aldol product and it is heated under acidic or basic condition, it results in an alpha beta unsaturated carbonyl, okay? And this is specifically called the Aldol condensation, okay? So this alpha beta unsaturated carbonyl is what we have right here. Understand that aldol condensations occur when an aldol addition is performed at elevated temperatures. So as you can see that if we have an aldehyde, because remember that aldehydes will be undergoing this aldol reaction, if you have base, water, but then we introduce the heat, then the favored product is going to be that alpha beta unsaturated carbonyl. So, to summarize the following reactions, if we have aldehydes, okay, specifically undergoing the aldol addition, remember that this reaction is accomplished if we have base and water. Okay? Aldol condensation specifically is we have base, water, and heat. And it's going to result in that alpha beta unsaturated aldehyde. Okay? Let's now go over the aldol condensation mechanism. So, in the aldol condensation mechanism, at least the first part of it, which is the formation of the aldol, is very similar to what we discussed previously. We have the base deprotonate the alpha position, is going to remove that alpha proton, and then we're going to have the carbon atom be negatively charged because it received the electrons between the carbon hydrogen bond. Then that carbon atom that is negatively charged is going to attack the carbon in the carbonyl in another equivalence of the reactant or of itself, if we think about it. Then once we form that alkoxide intermediate, it is protonated in the presence of water. So at first we're going to form the aldol. Then that aldol can be deprotonated at the alpha carbon for a second time, form specifically a carbon that now is holding a lone pair and is negatively charged. And what's going to happen, because again we are under basic conditions, then the lone pair at the carbon that is alpha is going to move and make that carbon-carbon double bond that I'm highlighting in magenta. And that's what makes the alpha beta unsaturated system. Now, whenever we are forming alkenes, we can envision that there's going to be two different forms. And understand that when two stereoisomeric pi bonds can be formed in a product, the one that is going to be the major product is going to be the one that is trans. Okay? The one that is cis, as you can see, that's going to be made as a minor product in the reaction. Now, let's take, for example, the following ketone, okay? Understand that specifically here, okay, because the aldol condensation is favored, we are not going to isolate that aldol isolate that you see in the middle. It's going to go all the way to form the alpha beta unsaturated system. So in this ketone, we are not going to be forming, okay, that aldol. Remember, we mentioned before that ketones have a hard time forming the aldol, but as you can observe here, is because they go all the way to form the aldol condensation product. So, to summarize, if we have a ketone, okay, the yields for condensation are typically much greater than the ones for addition. So in an aldol addition, which as you can see is the one in the top that yields to 20%, is going to have that aldol product be in much lesser amount. For the case of ketones, it is important to note that if you're under basic condition, and as you can see, heating the reaction to 100 degrees Celsius, what we're going to have in greater amount is the production of the aldol concentration, meaning that you're going to make the alpha beta unsaturated system.